All right. So now at the end of example 3, then for anyone who has been viewing through the entire example 3, you can see that the entire example 3, the kind of problems there are very popular kind of problem among all the problems finding limits at infinity. But unfortunately, it requires, these problems require a lot of algebra. But then, on the other hand, calculus is actually keep being applied and applied further and further into so many different professional fields out there, where unfortunately not all professional fields out there, people or experts there are fluent completely in algebra. And so over quite a few years recently there has been a good methods that been widely proven and accepted that are meant for the students who are on track, the students who are learning calculus but are on track into those kind of those professions where the not too much algebra are required. And so in this case right here, let me now introduce. So my plan now is I am going to give sort of like a second look at the entire example 3, but I am going now to introduce a much easier method to handle. And so any viewer who is viewing this video, you just have to know it for yourself, whatever kind of class you are in for calculus. So calculus, if you are in a calculus course that is meant for a formal math major or a formal engineering major or for a formal physics major, then you're going to learn through the techniques that I've shown previously in example 3 that has all the intensive amount of algebra steps. However, for students who are taking calculus, for example, business majors or health science majors, a lot of fields now outside of all the engineering field and mathematical fields now involve calculus. And so students who are in those professions or on track for those careers where not too much math required, then you can take and you can start learning and this easier methods to find the same kind to handle a lot faster the same kind of limits at infinity problem that were introduced in example 3. So now let me now make a look back at example 3 again. Okay, but then I would say, or how about let's informally call this, we're looking back to example 3. All right. And so right at the end of example 3, part A, and let me spend some time writing down part A right here. The function we had in part A was x squared minus 4x and divided by x to the 5th plus 3x squared plus 1. And our problem here is the problem that we would like to find limits of this entire, what I so called it, the rational function. So I want to find the limits as x was approaching positive infinity. But note that the method I'm about to introduce will also work for this, and it turned out it works the exact same and gives the same result as if you are doing to negative infinity. And so I mentioned in our actual example 3 that this entire function here is regarded as a rational function. And so let's say it's a polynomial in the numerator, and we have another polynomial in the denominator. And I also introduced briefly, but I believe enough, that each polynomial has a degree. And so what the observation now tells me that the degree of my numerator polynomial, or in short, as a shorthand symbol, again, the degree of our p of x polynomial is in this case, degree 2, is being less than the degree of our q of x polynomial. And that is simply because the degree for p of x is degree 2, and the degree for q of x in the denominator is degree 5. And so in that case, now if we recall right at the result right there that we have found by doing all, by going through all the algebra steps, then that answer here came out to be 1. And so that is exactly how it happens now. So anytime so in part A, I mean, another way of arguing it is, since our degree, and this method here is approved, is proven to be legal among all the work like that. So as long as our rational function satisfies that the numerator has lower degree than the denominator, then automatically the answer here, so our same exact rational function, x squared minus 4x divided by x to the 5th plus 3x squared plus 1. We don't need to do any calculation. We don't need to do any algebra as long as we recognize and be clear about our degree in the numerator is lower than the degree of the denominator. Then the answer will automatically, and it will be the same for any other rational function as long as this requirement or this observation is met. Okay, the answer is 0. Okay, so that answer here is exactly like the answer we've done that when we were going through formally example 3 in part A, but where I was going through all the algebra steps. But now, like as I said, if anyone viewing the video here is comfortable with going through all the algebras, you are more than welcome to use the algebra methods that was previously introduced in example 3. Otherwise, if you know your course that you are enrolled in is aimed at introducing you to calculus, but without requiring your definite mastery in algebra, then this method right here is completely welcome and being accepted among many a wide range of professors out there, including me. And so, well, for my own students, if I'm letting them to use this method right here to find the answer to a limit at infinity for a rational function like this, then the student is responsible to point out clearly that what they recognize or what they have observed. So this line is critical. So you got to indicate somewhere that what you recognize as p of x as a polynomial in the numerator, and what's q of x as a polynomial in the denominator. And be clear, be specific that you have observed that there's the numerator's degrees of the numerator is lower than the degree of the denominator. Okay. So we basically use the method, the easier method I'm introducing here is to be used based on directly on looking at the degrees of our polynomial. And so just like that, anytime now, I can guarantee that anytime the easier method now is that anytime we have a rational expression, a rational function, and our problem is a problem that is a limit at infinity problem, and we found out we have a polynomial on top being lower degree than our denominator being lower degree than our polynomial in the denominator, then the answer will automatically be 0. You can call it a shortcut, but it's a well-proven shortcut. Okay, so nothing illegal about that. Okay, so what about so now we're looking at the degrees being in the numerator at the top is being less than. So let's look at part B of our example. All right, so now in part B, the problem we had here was minus 3x cubed plus 1 and 4x cubed minus 2x plus 2. Okay, and that problem was a limit at infinity again. And so again, everything we're learning currently in this video lesson is about taking limits at when letting x go to infinity. Okay, either positive infinity or negative infinity. And so the method I'm showing here is good for either going to positive infinity or going to negative infinity as well. Okay, and so now I can go ahead and note that this numerator expression here is going to be my polynomial p of x. And notice that we have our degree here as being degree 3. And now our other polynomial in the denominator here is, we can call that now a q of x. So just make a label just to indicate that we've got two polynomials. And so now, the observation directly from this rational function is now giving us that the degree for p of x is indeed equal. So we run into a different case here. The degree in the numerator is indeed equal to the degree of the denominator q of x. Okay, and so let me grab a red pencil and I have to underline this. Now, the answer, if we recall, because I don't want to bring out the proof, it was actually this rule here, this truth we are using, this method we are proving was actually proven. And so, but of course, it makes no sense to show too much proof here, because we're going to lose all that practicality of the problem. So let's get straight into how useful that is and be able to use it. So note that so we call in the world of polynomials, then the values, the numbers in front of each x term is called a coefficient. So this is a coefficient. It's a coefficient. And these coefficients, they are the leading coefficients. Well, those, I hope at least, well, I'm trying to keep people, my students, without going back too far into algebra to review, but at some point you still need to remember a few the basic terminologies. So these are called the leading coefficients due to the reason that they are the coefficient of your highest term, the term with the highest degree. That's why it's called the leading term, and then the coefficient itself is called the leading coefficient. So I underline in red ink right here. So -3 is my leading coefficient of the numerator polynomial, and +4 is the leading coefficient of my denominator. And so now, if we're looking back at the answer we have already had for this problem back in example 3, then the case we notice here is that the degree of the numerator polynomial equals to the degree of the denominator polynomial. That answer gave us this answer. That problem gave us this answer: -3x cubed plus 1 over 4x cubed minus 2x plus 2. And as we took limits as x, letting x approaching positive infinity, our answer was a finite value, -3/4. And so now have a closer observation. This -3/4, -3 came out from -3 that I highlighted. I underlined here. 4 in the denominator of our final answer back in example 3, part B, came out from that leading coefficient in the denominator. And so as a generalization that was well proven and now being introduced for any of us here, anytime that we're taking a limits problem for x approaching positive infinity, and anytime we're recognizing that the degree in the numerator equals the degree in the denominator, then the answer can just simply be the ratio of the two leading coefficients. See, the -3/4 right here came out as a ratio. It's a fraction. So a ratio of the two leading coefficients, and stack them on top of each other as the exact same order how they started out. Okay, and of course at the end, after I thoroughly went through any of these, we're going to write down all of those generalization in words. Okay, and so let's now turn our focus. And again, before I move on to part C, to have a closer look at part C again, then if any of my students has decided to use this method right here, okay, then make sure to use this shortcuts method, even though now widely accepted. But if you have decided to use this method, your responsibility is to indicate on your written up solution that this is the line that leads to this quick final conclusion of your final answer. Because without this observation, we can't make, and there's no reason to support why we landed down to this other than doing the algebra. Okay. All right. So now I'm going to spend some time erasing my right-hand side board here, my other board, and let's consider the problem in part C. And I may have to bring up another extra one, similar to part C of our example 3 back then. All right, so here we go. So So now part C of our example 3 was we had a rational function where numerator was x to the 5th plus 4x cubed minus 1. And we're dividing that by x cubed plus 1. And this was a problem where we letting x approaching positive infinity. And that was part C of our example 3 that we were doing previously. Okay, and so again, with this method right here, the same method that we're relying on the degrees of the two polynomials on top and in the denominator here, at the top and at the bottom, then I have to first thing label. So this p of x right here is to indicate my numerator polynomial. And then I'm going to give a different name right here, q of x, as a polynomial that represents my denominator here. Okay, and so now in that case right here, well, in this particular problem, part C, what I recognize here is that the degree in the numerator is degree 5. Okay, and the degree at my denominator is actually only degree 3. So this time the observation here tells us that degree of p of x, my numerator polynomial, is greater than the degree at the denominator. Okay, so when this case actually happens, and again, the method I'm showing here is working for both going to positive infinity or negative infinity, the same way with part A and same way with part B right there. So, but in this worst case right here, well, I'm saying worse simply because it brings us a little more steps, a little more extra steps before we can make a final quick answer. But it's still faster than going through a whole bunch of algebra. So the degree here in the numerator is higher than the degree at the denominator. And so that means we won't have a quick answer yet. But instead, I'm doing this. The limit of the original problem, as far as the complete polynomials, x to the 5th plus 4x cubed minus 1 was the original polynomial in the numerator. And x cubed plus 1, we had only 2 terms in the denominator. But that original problem here is proven to be equal to the same limit problem. Okay, but now I have the ratio of the two. Now let me write it down before I explain. X to the 5th and x cubed. See, this is a fundamental result that was widely proven right here. It's actually also the truth that was also running behind the scene when I was explaining part A and part B, but you know, the earlier 2 cases already had landed into a quick answer, so I didn't even bother explaining this. But the idea now is that, well, let's find out where the x to the 5th and the x cubed came out from. Back to the original problem itself, the x to the 5th, now instead of just looking at coefficients, we're actually looking at the entire, so x to the 5th was the entire leading term of our numerator polynomial. And x cubed in the denominator here is the entire leading term of our denominator polynomial. And so what's the rule, what's the generalization we have found here that's being introduced here? Anytime the degree in the numerator is greater than the degree at the denominator, the first big step now is that it's guaranteed that this limit of the original rational expression will simply equal to the same limit, but of the ratio of the two leading terms. Okay, so the limit of the original rational function will be equal precisely to the limit, same limit, okay, of the rational function where it came out from being the ratio of the two leading terms. Okay, but then, well, for now it doesn't seem so helpful yet. It doesn't look so useful. But look at this. Now, the good thing about this now is that we can simply move on further step. X to the 5th over x cubed. You don't need to be super at algebra, but it's simple enough for you to cancel, for anyone viewing this video, to cancel the x to the 5th with x cubed right here, and we remain with a simple polynomial like this, x squared, and we're continuing to take limit as x approaching positive infinity. And then at this point, we can use our reasoning. We can use our reasoning that was introduced in the earlier part of the videos about how to find limits at the right-hand behavior of a polynomial. Simply what we ended up now is a polynomial. So let's find out. This polynomial is an even power and with positive leading coefficient. And so now the right hand here must grow to positive infinity. And so in that way, now I can say that my answer here is a positive infinity. Okay, because see again, I'm using that exact same reasoning as we have seen back in example 1 right there. Or maybe it could have been example 2 that I already forgot. Surprisingly, this is only part it's still in the same lecture, but I already forgot the order of my examples. But so see, even degree, it's a polynomial. The x squared, even though it's only one single term, but even degree with coefficient here, leading coefficient being positive. So that's why our end behavior is pointing up like that. Okay, all right. And so now allow me to bring up an extra problem very similar to this case of part C in our example 3, so that everyone can get real comfortable with the idea right there. Okay, and so now I'm going to swing to my other board and take a minute to erase it. And so let's say this is outside of example 3 now, but let's call it extra example. Okay, and so for this extra problem here, this extra example for everyone to see here, then let's say, and this one here, it's completely coming out from my instantaneous creativity, the creativity that comes right here, right now at this instant. So how about x to the 6 power minus 4x cubed plus 1? Okay, and we're looking at over x to the 3rd power minus 2x plus 1. Okay, and how about I'm going to put a 3 here with okay, a negative 3 there. Okay, and let's try to let's rely on our creativity and make the problem as crazy as we can. But let me now tell you how useful the rule we've learned is. So how about going to negative infinity? Okay, so here's what I observed. The numerator here, we can call that it's a polynomial p of x. The denominator here, we can call that it's a polynomial q of x. Okay, and so now again, I'm looking at p of x as a polynomial is having higher degree. So the degree in the numerator now is higher than the degree at the denominator. Okay, so that's observation must, and as I said again, if any viewer happen to be my students or to being students anywhere here and there, if you chose to go with this method, then make sure you got to indicate this line right here, because this line is the entire reasoning that leads to any of the later steps. Okay, and so now this line comparing the 2 degrees here is clearly indicating that our polynomial in the numerator is higher degree, higher than the one in the denominator. So that means based on what we have learned in part C of example 3, then our original problem. So now minus 3x to the 6 minus 4x cubed plus 1 divided by x cubed minus 2x plus 1. Okay, and we're taking that limit as x is approaching negative infinity. Okay, so this original problem will be exactly same result, same answer with limit as x approaching negative infinity again. Same limits problem. And this time, surprisingly, we ended up with much shorter rational expression. Minus 3x to the 6 over x cubed. All right. So where did these two come from? Negative 3x to the 6 was our leading term of the numerator polynomial. X cubed here was the leading term of our denominator, original denominator polynomial. And so now with this current final, it's a ratio of the two leading terms. Okay, and so now we can further reduce this algebraically, and as I said, up to this point, then even with very basic amount of algebra, you can still cancel things out just fine. X to the 6 cancel nicely with x cubed in the denominator, leaves behind for us minus 3x cubed. Okay, and now we want to take the limit as x is approaching negative infinity. All right, so now at this point, all of a sudden we realized that we turn our problem into the problem that considering the left hand behavior of a polynomial. And what's in this polynomial? It's a degree 3 odd degree polynomial with leading coefficient being negative. Okay, so let me remind you again, for polynomials being the odd degree polynomial and with leading coefficient, the negative leading coefficient, then the shape is going to look like this. Left hand behavior is going to rise and right hand is going to fall like that. Okay, and anything in between, we don't care. All right, so in that way, my final answer is ready. Since I'm looking at the left hand behavior, and then this polynomial satisfied the structure like that, odd degree, okay, with leading coefficient being negative, then my answer now for sure, you see that answer right there, it's pointing up as we navigating toward the left hand, and so our answer here is positive infinity, and that's how we find the answer right there. All right, and so now here we go. We are ready to make a formal formulation, a formal generalization of the easier methods that I'm introducing here. See, we solved the entire example 3 again, but in a much less amount of time. Okay. All right, so now I'm going to say let P of x and Q of x be polynomials. Okay, so any two polynomials here. So as long as we have that, then so now our problem is going to break into 2 to 3 different cases. Case number 1, okay. If the degree of P of x is less than the degree of Q of x, okay, then if we have that observation made, if we have that, now it becomes a condition of our statement here. So if we have that condition satisfied, if we have clearly indicated that observation, then this type of problem, a rational function is a ratio of any two polynomials. Okay, so the entire example 3 was all about any of those rational expressions, again, rational functions, a polynomial over a polynomial. And so then this kind of problem limits as x going to either positive or negative. So as a generalization, allow me to write plus and minus infinity to indicate that the method we're learning here works the same in any case right there. And we are particularly in that case where the degree on top is lower than the degree in the denominator. Okay, so now this limit here will quickly turn into a 0 for that first case. All right. And then now, in our second case, if the degree of our P of x is equal to the degree of Q of x, then, and I'm talking about particularly, I'm looking at, let's set out, generally in the entire generalization I'm doing here, then I want to set into that rule that P is on top and Q at the bottom. That's why it matters with these. Okay, so now when top and bottom have equal degree, then see, look back at what we have seen right there and what we have recognized. this rational expression where we keep p on top, q at the bottom, and taking the limits as x approaching either positive or negative infinity. Same way of working with that. Then the answer will be, no, it's not a, no, it's, how about let's put it this way. It's the ratio, okay, the answer will equal to the ratio of the two leading, but be careful, leading coefficients. Okay, and that's why, you know, again, keep flipping back. If you're taking notes, keep flipping back to your example 3, part B, and find out, see what I'm trying to understand what I meant by the ratio of the two leading coefficients. So that's the case number 2 right here. And so now, and there, that's how we have a limit. And now allow me to move on to my other board. I'm going to spend a minute to erase it. All right, here we go. So, case number 3 that we just now have seen. If the degree in the numerator is greater than the degree in the denominator. All right, then our limits problem of the rational function p of x over q of x, where the limits problem is a limit. It could be going to positive infinity or it could be going to negative infinity. But this problem now, it turns out to be, okay, so it's going to be, we're still going to produce the idea now that, and you have already seen it, the idea now is that it will equal to another, it's not quite directly the answer yet, but it will equal to another limit problem, and then that limit problem here will be a lot easier. It will be equal to the limit problem of, how about, let me call this some a of x to the n over some b of x to the m, okay? Where what are ax to the n and bx to the m? Ax to the n and b times x to the m are leading terms instead of leading coefficients. Now these are leading terms. Leading terms, okay, of p of x and q of x, respectively, in that order. So I write ax to the n first, so ax to the n is leading term of p of x, okay? And then same way b of x, the one in the denominator here is for q of x. That's what I meant by respectively. All right, so there you go. You have found that nice, solid methods that was it was proven, and the proof can be found somewhere here and there in many different textbooks out there on the market. But it's not, as I said again, it's not a practical thing to bring the proof here. And so, but we're gonna, it has so much to just simply use and enjoy how useful this result is. Okay, and so allow me to get back to my to the earlier part of this generalization, and let me add in a little bit thing here in case any viewer is going to be wonder about or being unclear about this. But so p and q be polynomials, and how about let me add in and, okay, and p of x over q of x. Okay, so I purposely now set clear that p of x over q of x is our rational function that we're considering the limits be a rational function. Okay, and And I apologize for the last minute correction, and it's making the writing a little tight to see, but you will understand.